On practice exam 9 of chapter 1 in the book Problem Solving with Differential and Integral Calculus. We have a right rectangular period. The base is W by L and the height is H. Its volume is LWH divided by 3. Let's focus on these one at a time. A is get the complete difference equation that relates delta V to L, W, H, delta W, delta H, and delta L. Let's tackle that one first. You're going to need a new page because we need a lot of space. The normal equation is given. The difference equation, the volume changes when L, W, and H change. So there's the volume equation. First going to FOIL out the first two terms. And then we're going to distribute the H plus delta H in there. And that gives this mess. You should be able to spot the original volumes on each side. There's one, and here's the other one. 1/3 H, L, W. That's the original volume, so that we can get rid of those. And we have delta V. That's the answer to part A. You should be able to pick out the linear terms and the nonlinear terms. On to part B. Part B, we have specific dimensions. Pyramid 1 is 3 by 3 by 4. Pyramid number 2 is 4 by 6 by 6. And we're going to use the normal equation twice to get the volume difference. This is pretty straightforward. No calculus involved here. We're going to plug in 433 and we get 12 cubic feet for the volume of the pyramid number 1. Pyramid number 2 has a volume of 48 cubic feet. The difference, we subtract them and we get 36 cubic feet. Part C asks us to get the difference in their volumes using the difference equation. And there's going to be linear terms and there's going to be nonlinear terms, and you probably know how much the nonlinear terms are going to contribute, roughly. So there's the total equation. The linear terms are the ones with only one change. So delta L, the first three terms, you only have one change in them. Here we're multiplying 2, and then here we're multiplying 3. So those are the variables, and we're going to use the changes this time. Here's the linear part, sticking those in. There's the nonlinear part. And I'm going to put a nice table over here so we have them available easily. The linear part is this, and you can see that the changes here, delta L is 2 feet, delta W is 3 feet, delta H is 1 feet, are not that much different than the dimensions themselves, so we can expect the nonlinear term to contribute significantly. The linear term, doing the math, is 22 cubic feet, and then we plug in all the numbers for the nonlinear term, and we get 14 cubic feet. So the total volume difference is the linear plus the nonlinear contributions, and you add those up, you get 36 feet cubed, and that's what we got last time. On to part D. Part D is using only the linear terms in the difference equation. Calculate a very good estimate of the percent change in the height of the pyramid that will result no change in its volume when both W and L are increased by 1%. This is a nice calculus problem. We're increasing W and L by 1%, and we don't want the volume to change. So if we're going to make W and L 1% bigger, we have to shrink the height to keep the volume the same. So the question is, how much do we have to shrink the height? By what percentage do we have to change the height? So we're starting with H, W, and L. We want delta V to be 0 when delta W is 0.01 W. That's a 1% change. We could also write W divided by 100. Delta W is W over 100. Delta L is L over 100. 1/100th of L, which is 1%. We need to calculate delta H. And we're just going to use the linear term. It's going to be an approximation. We're throwing out, it's pretty small. It's only 1% change. So it should be close. Not like before. So here's the linear term. What do we plug in for delta L? We plug in 0.01 L. So we have no numbers for anything. We just have percentages. We're solving for delta H. Delta V is 0. and delta L is 0.01 L, delta W is 0.01 W. Now we can divide both sides by the original volume of the pyramid. So we have HLW here, HLW here. So here's what it looks like. The left-hand side still 0 when you divide by 1/3 HWL. So the 1/3 will cancel. And right here, the first term is only 0.01. The second term is only 0.01. The third term is delta H divided by H. The 1/3 cancel, the L's cancel, the W's cancel. So 0.01 plus 0.01 is 0.02. Now we have to solve for delta H. So we put the 0.02 on the other side by subtracting 0.02 from each side, and we multiply the H over there too. And we get delta H is minus 0.02 H. So yeah, delta H is 2%, negative 2% of H. If you shrink the height by 2% and increase W and L by 1%, the volume will be roughly the same. Remember, we threw out the nonlinear terms. So we have to reduce the height by 2%, and that's the answer to part D. But let's keep going because we want to check this. Let's use the normal equation to check this. What's delta H exactly when both W and L are increased by 1% to have no change in volume? So there's the original volume. The new volume is this, but we can set these equal because we don't want the volume to change. And then solve for delta H. So there's the original volume, there's the different volume. Solve for delta H. So we get rid of L's and W's, those cancel. We have this H equals this. We can collect the H's, solving for delta H. And we get minus 0.0197 H. And we can have as many significant digits as we want because this is exact. I only kept 4. But this is very close to minus 2%. So we're very happy with this. We left off the nonlinear term. We're close enough. Minus 2% change to keep the volume the same.